Assalamu alaikum class. I hope that all of you are well and safe in your homes inshallah. Lecture 37 of our course Signals and Systems is going to introduce the concept of discrete time Fourier transform or DTFT. Just as the continuous time Fourier transform was used to observe the spectrum of continuous time is periodic signals, the discrete time Fourier transform is going to be used to observe the spectrum of discrete time aperiodic signals. We'll see the conditions of existence of DTFT, also termed as convergence, in your book. Finally, we'll see that just as CTFT can be used to observe the spectrum of periodic signals, the DTFT can also be used to observe the spectrum of periodic signals. So DTFT or the Fourier transform is a general technique which is used to observe the spectrum of both periodic and aperiodic signals, although it is originally derived for aperiodic signals. DTFT is the final of Fourier analysis techniques that we are going to study in our course. The discrete time Fourier transform can be derived from discrete time Fourier series. In a similar fashion, continuous time Fourier transform was derived from continuous time Fourier series. By definition, for a finite duration sequence x of n, the DTFT is given by x of e j omega is equal to summation over all values of n from minus infinity to plus infinity, x of n x times exponential minus j omega of n. This equation is used to observe the spectrum of x of n, therefore it is also known as the analysis equation. We also observe that whenever we have a discrete time spectrum, the spectrum for a discrete time signal, we represent it by x brackets exponential of j omega, whereas for the spectrum of a continuous time signal, we express it as x of j omega or x of omega. The Fourier transform, the x of e j omega, is termed as the spectrum because it provides information of how xn is composed of complex exponentials of different frequencies. The inverse discrete time Fourier transform or the synthesis equation is given by x of n is equal to 1 by 2 pi, an integration between 2 pi for x of e j omega exponential of j omega n d omega. Now we see that in this synthesis equation we are integrating over an interval of 2 pi and not from minus infinity to plus infinity. So this equation indicates how an aperiodic sequence can be thought of a linear combination of complex exponentials, but since these complex exponentials are very close in frequency, so the summation is not used and integration is used, and the amplitude of the complex exponentials is x of e j omega d omega by 2 pi. The difference between CTFT and DTFT lie because of this interval 2 pi, because this has a finite interval of integration in the synthesis equation. Discrete time Fourier transform is periodic. It is periodic over an interval of 2 pi radians. The reason for DTFT to be periodic is because of being multiplied by the complex exponential e j omega n. Since this complex exponential is a discrete time complex exponential, and we know that discrete time complex exponentials which differ in frequency by a multiple of 2 pi radians are identical, therefore DTFT is unique only within the interval 0 to 2 pi. That is why in the synthesis equation to determine x of n, we were integrating over an interval of 2 pi. So to see a demonstration of how the DTFT is determined for a discrete time sequence, let's consider this simple example where a gate or pulse function is shown. This function is defined as x of n is 1 for n is less than equal to n1 and it is 0 otherwise. Such a function can also be written as gate n by 2 n1 or rect n by 2 n1, where the width of the pulse comes in the denominator of n. This is the same way a continuous time pulse or gate function was defined, either through a rect or through this gate symbol or through definition. So using the definition of Fourier transform, the limits of summation are modified from minus n1 to plus n1, which is the interval over which our signal is defined. Now if we observe this summation, we know that it is easier to solve the summation if the lower limit of the summation is 0. So we'll adjust variables in such a way that the lower limit of integration becomes 0. So we take this n1 on the other side of equality, this minus n1, and we say that n plus n1 is equal to m, which implies that n is equal to m minus n1. Now when n will be equal to minus n1, we'll substitute in this value minus n1 plus n1, therefore our m will be 0. And for the upper limit, when n is equal to capital N1, m is equal to n1 plus n1, which is 2n1. So substituting the values of n in the equation, we have the limits of summation varying from 0 to 2n1, and over here we have replaced n by this m minus n1. Now since the summation is not dependent on n1, we take n1 outside the summation sign and apply the summation over the term inside the summation sign, and we get e raised to power minus j omega n1 1 minus e raised to power minus j omega 2n1 plus 1, which is how we apply the sum of finite geometric series divided by 1 minus e raised to power minus j omega. Manipulating the variables, multiplying this inside and solving it brings us to x of e j omega is equal to sine omega n1 plus 1 by 2 by sine omega by 2. Now whenever we have a sum of or difference of complex exponentials, it is easy to convert that sum and or difference into sine or cosine terms, because it is easier to plot the function and the terms or the value, the result takes a more compact form. However, if you give me this value as the result x of e j omega, I am okay with that as well. I have just converted this value into sine terms because it is as is done in your book, and for you to determine the value of x e j omega for different frequencies, you will be substituting the values in just one expression for the numerator rather than two times in the exponentials. So solving this equation is generally easier. A tip for solving such an equation is whenever we have a sum or difference, we must know that we take half of the term outside the bracket, so 1/2 appears with each complex exponential, so it's easy to solve. So after solution, we have x of e j omega is equal to sine omega n1 plus half by sine of omega by 2. Now let's observe the spectrum of the signal. For plotting the spectrum, let's assume that n1 is equal to 2, so that x of e j omega simplifies into sine 5 by 2 omega divided by sine of omega by 2. Now to plot the spectrum, we have to vary the frequency omega in certain intervals over the range minus pi to pi. So let's plot the positive frequencies first. The omega interval or the spacing between the frequencies can be any frequency of our choice. Over here I am taking pi by 8 as the difference in frequency or the frequency interval. So let's say when we have omega is equal to 0 x of each omega will give a value of 5 by using L's hospital rule, because it is sine 0 by 0, which is of the form 0 by 0. We have done this many times. To solve it, we take the derivative of both the numerator and the denominator and substitute the limit omega is equal to 0. So this becomes 5 cos 5 by 2 omega into divided by cos of omega by 2, and when you put omega is equal to 0, we have 5 from the numerator remaining. When omega is equal to pi by 8, we get this value, and we'll see that the value is maximum at omega is equal to 0. It decreases, and after reaching a certain negative value, it again increases. Now if we have to determine the zero crossings of this function, we know that the zero crossings will occur when the numerator is 0. So the numerator is 0 when 5 by 2 omega is a multiple of plus minus n pi, or omega is equal to 2 by 5 n pi. So the first 0 would be at 2 by 5 pi, second 0 will be at 4 by 5 pi, which is 0.8 pi. If I had taken the interval as between the frequencies at pi by 10, then we would have easily observed the zeros. The way I am plotting it, it's not the zero crossings will be visible, but it's the exact location will not be obvious to you. So I leave it as an assignment that you will take the interval as omega is equal to pi by 10 and try plotting this function again by yourself. So plotting these values, we have a form like this, where at omega is equal to 0, the value was x each omega was 5. When the value of frequency was pi by 8, we had a value 4.262, and so forth. So the positive side of the spectrum is plotted between 0, omega is equal to 0, to omega is equal to pi. This point is 8 pi by 8, which is pi. When we vary frequencies on the negative side, we will observe the same values as the positive frequencies, and this is what is expected, because we know that Fourier transform, in Fourier transform the magnitude is always even symmetric. So for this function, although we are not dividing the spectrum as magnitude spectrum and phase spectrum, because the spectrum is real, so the phase for this is 0, and it is just the magnitude spectrum which exists. But we know that the spectrum could have been divided into magnitude spectrum and phase spectrum, and if the spectrum was divided into magnitude and phase, then for this positive values we get a phase of 0, and for the negative values we get a phase of 180 degrees. So we see that the magnitude spectrum is even symmetric. Now what happens if we vary the frequencies beyond pi, say from pi to 2 pi radians? This is a reproduction of the plot on the previous slide between minus pi to pi. So when we vary the frequencies for omega beyond pi to 2 pi radians in same intervals of pi by 8, we'll observe that the values are 0.566, minus 0.419, minus 1.18, and so forth. So this portion of the graph is obtained. Now if we look at both these two graphs, we can say that this graph can be derived from this graph or vice versa, because we know that discrete time exponentials are periodic with a period of 2 pi. So this minus pi frequency is actually equal to minus pi plus 2 pi, which is pi. So this entire plot comes up to here. This portion comes over here, because the frequency at say 0 is 0 plus 2 pi, which is 2 pi. So if we have a plot or if we have a range, if we have a values over the range 0 by pi, we can easily obtain the plot from minus pi to 0 or from pi to 2 pi. But since we know that x of e j omega is periodic, so the overall plot will look like this. It will continue over all range values of omega, and it will be periodic over a period of 2 pi obviously, but it will continue for good. The DTFT was derived assuming that we have a finite duration sequence. So the definition of DTFT was for a finite duration sequence. However, the Fourier transform is a very powerful tool, and it can be used to observe the spectrum of infinite duration sequences as well, provided the signals meet certain conditions known as the conditions of convergence. So the conditions of convergence say that the analysis equation or the DTFT transform equation will converge if these two conditions are met, which are that the signal converges, that is, x of n has a finite value when you sum it, when you sum the magnitude values over the entire range of the signal, and the sequence has finite energy, which is when you take the magnitude square for all the values and add them over the entire duration of the signal, you get a value which is less than infinity. Generally, you will see that for signals where the value of x of n is such that x of n, the magnitude of x of n reduces as n approaches infinity or as n increases, those signals will be having a Fourier transform. These conditions need to be met for the analysis equation. However, for the synthesis equation, there are no convergence issues because the integral is determined for an interval of 2 pi. So the conditions of convergence need to be met for determining the Fourier transform only. Let's solve an example and determine the DTFT of an infinite duration sequence. We have an infinite duration sequence given as x of n is equal to a raised to the power magnitude of n, where a is less than 1. So when we plot the signal over the entire duration from n is equal to minus infinity to plus infinity, we get a shape like this. This is because of a being less than 1, which means that for higher values of n, you are basically taking higher powers of a fraction, which implies that the fraction becomes smaller and we get smaller values of magnitude. We can see that it is possible to determine the Fourier transform of such a function because the magnitude or the value of the function decreases as n increases. So on either side of n, whether n approaches plus infinity or n approaches minus infinity, the magnitudes take a diminishing value, they become increasingly small, and hence we can see that the condition 1 of convergence is met and the value of the summation converges. You must have noticed from the plot of x of n on the previous slide that x of n is even symmetric, or it's an even function of n. So to determine x of e j omega, we substitute the values in the formula and we get n is equal to minus infinity to infinity, a raised to power magnitude of n, e raised to power minus j omega n. Now we'll be dividing the summation into two parts. For the first part, the summation will vary from 0 to infinity and we have a raised to power n, and for the negative part we have a raised to power minus n, and the summation will vary from n is equal to minus infinity to minus 1. Now this latter summation, we have to convert it into a range from 0 to some value because as discussed earlier, it is easy for us to solve sum of finite geometric series where the value varies from 0 to some number. So I exchange the order and order of these two summation terms. I bring this term over here and take the n outside the brackets so that it is easy to change the limits. Now when I solve, I have n is equal to 1 to infinity ae j omega n plus n is equal to 0 to infinity ae minus j omega n for the positive values of n. So for this summation to start from n is equal to 0, let's say that n minus 1 is equal to m. This implies that n is equal to m plus 1. So when n is equal to 1, m is equal to 0, and when n is equal to infinity, m is also equal to infinity. Substituting the values and observing that the summation depends on m only, so this term with power 1 gets outside the summation. Applying the formula and solving the values, we get x of e j omega is equal to 1 minus a squared divided by 1 minus a e raised to power minus j omega plus e raised to power j omega plus a squared. Now, like I explained for example 1, it is whenever we have a sum or difference of complex exponentials, it is easy or it is simpler to convert it into a sine or cosine term. So we'll be converting this term into a cos term, and this is the resultant expression, compact expression for Fourier transform. X of e j omega is equal to 1 minus a square by 1 minus 2a cos omega plus a square. Now this value of x e j omega is real. Now for both example 1 and 2, we have one inference to draw, that both sequences in example 1 and 2 were real sequences and they were even symmetric, and for both the sequences the Fourier transform was real. So we can have this inference that for even symmetric signals the Fourier transform is real. Now let's plot the spectrum and see what frequencies are obtained by this sequence x of n. So to plot the spectrum, we have to assume a value of a. Since the value of a varies between 0 to 1, so let's say that the value of a is 0.5. So at frequency omega is equal to 0, substituting the frequency in the expression for x of a e j omega, we get 1 plus a by 1 minus a, which is equal to 3. So again, like example 1, I have varied the frequency in intervals of pi by 8 from 0 to pi, and the values of x of e j omega are obtained. So shown over here is a plot of these values for frequencies from 0 to pi, and we can see that the function's value decreases till omega is equal to pi. Now if the value of the function is desired for the frequencies from 0 to minus pi, then by symmetry, which we just discussed, the shape will be like this. Here the value is kind of appears to increase, although it does not. This is because I cannot control this pen very comfortably in Windows. But over here the plot is going to be something like this. So if we plot the frequencies, or if we plot the spectrum over the entire frequency range, this kind of a shape will be obtained. And we know that this plot will continue from omega is equal to minus infinity to plus infinity, although it will be periodic with a period of 2 pi. The Fourier transform in general is a very versatile tool. It can be used to determine the spectrum of aperiodic, finite time and infinite time sequences. However, it can also be used to determine the frequency spectrum for periodic sequences. So, similar to the continuous time case, discrete time periodic sequences can be incorporated in the DTFT framework by thinking of the DTFT of periodic sequences as an impulse train in the frequency domain. so that the spectrum we obtain is a line spectrum. So if x of n is a periodic sequence with discrete time Fourier series coefficients given by a of k, then the Fourier transform pair for x of n takes the form x of n is equal to summation over n ak ejk omega naught n, where omega naught is the fundamental frequency and ak is the magnitude of the Fourier series coefficients. Similarly, the analysis equation or the Fourier transform equation takes the form x of ej omega is equal to 2 pi, k varies from minus infinity to plus infinity, ak del of omega minus k omega naught, where omega varies from minus pi to pi, since we know that DTFT is periodic with a period of 2 pi. So this implies that the Fourier transform of the periodic signal is going to be a line spectrum as expected, because it will only take the range of values where k is an integer. So it will be occupying the fundamental and multiple frequency, and its multiples are fundamental and the harmonic frequencies only. So we can interpret that the Fourier transform for a periodic signal is a train of impulses with weight equal to 2 pi times the kth Fourier series coefficient a of k. So as the final example for this lecture, let us determine the DTFT of the periodic signal x of n is equal to cos of omega naught n, where omega naught is given by 2 pi by f. Since x of n is given by cos of omega naught n, I will derive the Fourier transform for general case and eventually I'll substitute the given frequency. So we open x of n by using Euler's formula and we get two exponentials. From our knowledge of Fourier series, we can see that for this exponential k is equal to plus 1 and for this exponential k is equal to minus 1. So we have two frequency components at k is equal to plus minus 1, and the value of Fourier coefficients at these frequency components is a1 is equal to 1 by 2 and a minus 1 is 1 by 2. Since both these frequency components are at fundamental frequency or at omega naught is 1. Now x of ej omega by definition is 2 pi k minus infinity to infinity ak del of omega minus k omega naught. So substituting the values of ak, we get 2 pi half del of omega minus omega naught, because k is just 1, plus half del of omega plus omega naught. Substituting the values of frequency, we get pi del omega minus 2 pi by 5 plus pi del omega plus 2 pi by 5. This value signifies to an impulse at frequency omega is equal to 2 pi by 5, which is this impulse, and this value signifies an impulse at frequency omega is equal to minus 2 by 5, which is this impulse. This expression for Fourier transform is given between the range minus pi to pi. So if we want to observe the entire spectrum, we know that the spectrum repeats itself. So replicating this side of the spectrum after 2 pi at minus 2 pi and so forth. So for this impulse, we get an impulse over here, and the value of this impulse is 2 pi minus 2 pi by 5. So this impulse appears here. For this point is also equivalent to 0 minus 2 pi. So this point is the same as this point, and the impulse, this impulse appears here. So the spectrum will keep on repeating itself, and we'll be getting an impulse train as shown. This figure shows a general case of omega naught. So as we discussed on the previous slide, this impulse repeats itself after every 2 pi radians. So all these impulses are the same, where we can observe that the gap or the duration of this impulse is 2 pi radians, whereas the impulse due to negative frequency this and this and this is the same, where again the difference between them is 2 pi radians. So whenever you see a periodic spectrum, it will imply that it is the spectrum of a discrete time signal, and for a periodic signal the spectrum x of e j omega will always be a discrete spectrum, whereas for an aperiodic signal the spectrum x of e j omega will be a continuous spectrum. So in this lecture we have seen how to determine the discrete time Fourier transform for a variety of discrete time signals, which included aperiodic finite length signals, aperiodic infinite length signals, and periodic signals. We have seen and learned how to plot spectrum, Fourier spectrum, and we have observed that the Fourier spectrum is periodic. So if we determine the spectrum for 0 to pi in certain intervals, which is our choice, the same spectrum can be repeated for pi to 2 pi or from minus pi to 0. So now I'm sure after this lecture it will be easy for you to draw a periodic spectrum. For today's lecture, in case you have any problem or query, you can always email, text or call, and I'll sure be responding to you. Wishing you best of studies. Allah Hafiz.